Lesson 29, the Central Limit Theorem. When a sample of n independent data values are randomly selected from a population with 1. Any shape distribution, 2. Any mean mu sub x, and 3. Any standard deviation sigma sub x, the sampling distribution of the sample mean x bar has 1. An approximate normal distribution, 2. A mean mu sub x bar equal to mu sub x, and 3. A standard deviation sigma sub x bar equal to sigma sub x divided by the square root of n. So the focus of the central limit theorem is on the sampling distribution of the sample mean x bar. So the central limit theorem provides the information necessary to calculate probabilities involving x bar. These are done under certain conditions. That is, when a sample of n independent data values, where n is the sample size, and independent means that the random selection of one data value does not affect the random selection of another, are randomly selected from a population with any shape, any mean, and any standard deviation, thus meaning that the central limit theorem results apply to any population. This gives the central limit theorem a great deal of power. That is, we can take our random sample from any population, and the results of the central limit theorem still apply. Now, the results of the central limit theorem tell us that the sampling distribution of the sample mean x bar has 1. An approximate normal distribution. This means that the normal probability distribution is used to approximate probabilities involving the sample mean x bar. Also, they're approximate. It turns out that as the sample size increases, the approximation becomes more accurate. So with a larger sample size, you have more data, and with more data, the results become more accurate. As it turns out, in the approximation, the closer that the population resembles a normal distribution, the better the approximation becomes. So the sufficiently large sample sizes are different depending on the shape of the population. The closer the population is to being normal or bell-shaped, the smaller the sample sizes are needed to still get very good approximations. But the more that the population deviates from a normal bell-shaped distribution, the larger the sample size has to become in order for these approximations to become closer. Also, the mean, mu sub x bar, of the sample mean is the same as the mean for the population from which the sample was collected. Now, the mean is calculating the center or balancing point of the data. So the sample mean is trying to calculate the same center as mu sub x, the mean of the population. Thus, with good representative random samples, the sample mean x bar is really trying to calculate what the population mu sub x value is. And with the standard deviation of the sample mean is the population standard deviation divided by the square root of the sample size. So the standard deviation is not the same as the standard deviation for the population. What it is it ends up being smaller by a factor of dividing by the square root of n. Well, these results of the central limit theorem can be illustrated with the following examples. In the central limit theorem, a random sample is selected from a population. So with a random sample selected from a population, we then take these data values and calculate the sample mean x bar. The sample mean x bar is that center or balancing point of the data. So even though we have a random sample with scattered random data, the sample mean x bar is always calculating that center or balancing point. Now, this is done regardless of the shape of the population. The population can be normal or bell-shaped, or it could be skewed right, or it could be skewed left, or it could be multi-bell shaped. It doesn't matter. we still take this random sample from the population and calculate the sample mean x bar. Now the results of the central limit theorem tell us how the sample mean x bar behaves. So if we were to take another sample from our population, so another completely different random sample from the population, and then calculate the sample mean x bar, we still basically get the sample mean x bar as our measure for center or balancing point. So even though we have different data values, the sample mean x bar is still trying to calculate the same result, that value in the center. So again, taking another random sample from the population and then calculating the sample mean x bar, the sample mean x bar pretty much always occurs somewhere in that middle or center value. Sometimes the data values are close together. Sometimes the data values are far apart. But regardless, when we calculate the sample mean x bar, the sample mean themselves is always indicating that center or middle balancing point. Now, sometimes by chance, we just happen to get a few higher data values and not as many lower data values. In that case, the sample mean x bar is slightly higher than the center. This can happen just by chance. But overall, even though the sample mean may not be exactly equal to the population mean in every individual sample, it's always going to be somewhere close. We could take a sample where we have slightly more lower data values and not as many higher data values. In that case, the sample mean will be slightly lower than the center. But still, the sample mean, calculating the center of this particular sample, is close to the center for the overall population mean. So, random samples, we get different results. Sometimes we get a few lower data values, not as many bigger data values, and again, the sample mean would be slightly lower. Again, it doesn't matter what the population is. The population could be any shape, and still when we take the mean from the sample from this population, we sort of get results that are somewhat in the center. Now, sometimes we get most data values that are much lower, and not very many at all that are higher. This will give a much lower mean or center balancing point for the sample. But this doesn't happen very often. Whenever we do represented random samples, by chance we could get these data values that are mostly lower, but it doesn't happen very often. Same thing, we could take a random sample and just by chance happen to get mostly all larger data values, thus leading to a sample mean that is much larger. But the chance of getting mostly all larger data values leading to a larger sample mean doesn't happen very often. Typically, the random sample gives representative results that are randomly scattered across the entire population, and when we calculate the mean for that sample, it always ends up usually somewhere in that center, the middle or balancing point. So, as a result, we can see that the sample means tend to have an approximate normal or bell-shaped distribution. That is, most of the time the means will cluster around the center. But every once in a while, the means are sometimes lower or higher, but that doesn't occur too often. So the sample mean, which is always trying to calculate that center, most of the time we get the results in the center. But by chance, every once in a while, sometimes we get values that are a little bigger, or sometimes values that are a little smaller, but that doesn't happen too often. Thus, this leading to the pattern of the low, high, low, that is a normal or bell-shaped distribution. So, the sampling distribution of the sample means approximately follows a normal or bell-shaped distribution. Regardless of the distribution of the population, the distribution of the sample mean has an approximate normal distribution. When the sample size is sufficiently large, this approximation becomes very good. Now, the other results of the central limit theorem tell us that it doesn't matter what the population is. These results still apply. That the sample mean is always trying to calculate that middle or center value. And by chance, sometimes it's a little lower, sometimes a little higher, but overall, the distribution of the sample mean has an approximate normal distribution. Now, the mean of the sampling distribution of the sample mean is equal to the mean of the population from which the sample was collected. That is, mu sub x bar equals mu sub x. The other conclusion regards the standard deviation. The standard deviation of the sampling distribution of the sample mean is equal to the standard deviation of the population from which the sample was collected, divided by the square root of the sample size. That is, sigma sub x bar equals sigma sub x divided by the square root of n. These two results of the central limit theorem can be demonstrated mathematically as follows. So mu sub x bar, the mean of the sampling distribution of the sample mean, is equal to the expected value of x bar. Now x bar, the sample mean, is calculated by finding the sum of all the data values and dividing by n how many data values were collected. One of the properties of the expected value function is that when we divide by a constant within the expected value function, we could divide by that constant outside the expected value function. Thus here we can write it this way. The expected value of the sum of the data values can be divided by n when the sample size n is a constant. Another result of the expected value function is that here we have independent collected data. And with independent data, where one does not affect the other, the expected value of the sum of the data values is equal to the sum of the expected values. In addition to having the condition of independent data values, we also have identically distributed data values. That is, each of these data values come from the same population that have the same mean. So the expected value of each one of the individual data values is equal to the mean mu sub x of the population. And here, if we are adding the mean mu sub x n times, we have n times mu sub x, which is being divided by n, and the n divided by n equals 1, and 1 times mu sub x equals mu sub x. Thus, we've demonstrated how mu sub x bar is equal to mu sub x. Now, to do this for the standard deviation, we need to introduce a function for standard deviation, which is the variance. The variance of a random variable x is the square of the standard deviation. It is denoted by v of x equals to sigma squared sum x. Consequently, the standard deviation of a random variable x is the square root of the variance. That is, sigma sub x is equal to the square root of the variance of x. So the variance is just the square of the standard deviation, and the standard deviation is just the square root of the variance. So here, using the variance function to help us find the standard deviation of the sampling distribution of the sample mean x bar, we could show that sigma sub x bar is equal to the square root of the variance of x bar, where x bar, the sample mean, is the sum of all the data values divided by n, the total number of data values added. Now, a property of the variance function is, since the variance involves the squaring of the standard deviation, if we are dividing by a constant within the variation function, we can divide by the square of that constant outside of the variance function. So for a given sample size n would be constant. So we could take the variance of the sum of the data values and divide it by n squared. Now, another property of the central limit theorem tells us that the data values are independent of one another. And when the data values are independent of one another, the variance of the sum of the data values is equal to the sum of the variances of the data values. In addition to being independent data values, they're also identically distributed. That is, these data values were sampled from the very same population that have the very same variance. So the variance for each of these individual data values is equal to the variance of the population. So we have sigma squared sum x being added n times. And sigma squared sum x added n times gives us a result of n times sigma squared sum x, which is being divided by n squared. So the n in the numerator divides out just one of the n's in the denominator, and we're left with sigma squared sub x divided by n. Now to get the standard deviation, we just take the square root of the variance. And the square root of the sigma squared sub x is sigma sub x divided by the square root of n, thus demonstrating how sigma sub x bar is equal to sigma sub x divided by the square root of n. So the central limit theorem can be used to calculate probabilities involving the sample mean x bar. So under the conditions of the central limit theorem, the normal probability distribution can be used to approximate probabilities involving the sample mean, x bar. For the TI-84 calculator, this means that we can use the very same commands that we use for any normal probability distribution problem, the normal CDF command and the inverse norm command. The normal CDF command and inverse norm command are used in the same way for any normal probability problem. The only adjustment is when we're dealing with the sample mean x bar, the standard deviation, sigma sub x, is divided by the square root of n. Other than that, the normal CDF and inverse norm command on the T84 calculator are used in the same way to solve these normal bell-shaped curve problems.